Video, we will cover section 8b, which is all about doubling time and half-life. So recall that anything that grows constantly at a relative growth rate is exponential. So an example, something grows 6% per year. Then we know that we let the R value equal 0.06. If R is equal to 100%, then we're modeling doubling time. So doubling time is just a special case, really, I should say, of exponential growth. The formula that we use for doubling time is Q is equal to Q naught, look familiar, times 2 raised to the little t over big T double. Q naught is our initial amount. And this whole thing is in the exponent. The little t is our input for time. Big T double is given in the problem, and it's the doubling time. Just like in the previous section, make sure that these two units of time are in the same unit. We have a handful of examples here. Let's try example 5. Example 5 says, the world population doubled from 3 billion in 1960 to 6 billion in 2000. Suppose that the world population continued to grow after 2000 with a doubling time of 40 years. What would the population be in the year 2050? And then, of course, the second question, a follow-up, what would the population be in 2200? Let's start with 2250. So we know that it's doubling. Let's write out our equation. Q equals Q naught times 2 raised to the little t over big T double. Now it doubles every 40 years after the year 2000. So we're going to say that the year 2000 is time 0. So in other words, time starts at 2000. It told us that the doubling time is 40 years. So our T double will be 40. And it told us that at the year 2000, that the total population is 6 billion. So that's what we're going to use as our initial value, our starting value. We're modeling from the year 2000 on. So Q naught is going to be 6 billion. I'm just going to write 6 here, and I know that my answer will be measured in billions. You could always multiply by 1 billion afterwards. And so we'll plug it all in. And it asks us first, what will the population be in the year 2050? Well, since time starts at 2000 and we're interested in what's happening 50 years later, we're going to say that little t is 50 for this example. So we plug it all in. We have Q is equal to 6 times 2 raised to the 50 over 40. If you're going to do this whole thing in your calculator at once, make sure to put your exponent in parentheses. I do 6 times 2 raised to the, I'm going to put another set of parentheses for my exponent, 50 over 40. And close my parentheses. In this case, when I round maybe to, I'm just going to round to 1 decimal place. And I'll say that that's the same as 14.3. Or in the year 2050, we expect the world population to be 14.3 billion. So what about in 2200? Well, the process is going to be the same, except now our little t is 200. instead of 50. So in 2200, little t is 200 years later. Our Q naught is still the same. The initial value was 6 billion. T double doesn't change either. T double was 40 years. Just as some background for this particular problem, the period of time between 1960 and 2000 had an extremely high rate of growth around the entire world. That was post World War II. Things had begun to settle down. People came home. Lots of babies were made. So it's not necessarily going to be something that we can extrapolate over 200 years to say, oh, we're going to continue growing this way. But let's just see what happens if it continued to grow this way in 200 years. We have Q is equal to our starting value 6 times 2 raised to the 200 over 40. In my calculator, I plug in and I get 192 billion people, which is not possible. We don't have enough resources on Earth to house 19.2 billion people. Currently, we have just over 7 billion people now, and lots of scientists have said somewhere around 10 to 15 billion is when we're going to start leveling out and running out of resources. So this actually brings up something important about exponential growth. No exponential growth can continue forever. It's simply not possible because we don't have the resources for that to continue going on. We see this phenomena a lot in population growth, in bacterial growth, in epidemics, all sorts of different things. And what ends up happening is we get this curve that increases really, really fast. This is the exponential part of it. And then at some point, we have this limiting factor that comes in and it creates this point in which we stop growing exponentially and we begin to slow down. And what we slow down to is ultimately some ceiling that allows us, that we're not allowed to cross, that allows us to come in for a landing. And that ceiling obviously can change over time, but depending on our resources, it's not going to increase indefinitely. When a curve does this, this lower part here we refer to as the exponential part, but in general, when we see a curve this way, we refer to it as a logistic curve. And actually, this is where we get that short phrase log from. So we have this logistic curve, logarithmic curve that's going on right here, and it allows this thing to bend over time and come in approaching some upper bound. So I imagine somewhere between this number from 2050 and this number from 2200, we would run into a place where the population begins to gradually slow. Another important formula to doubling time allows us to look at the rate of increase and determine how long it takes for something to double. So this formula is T double is equal to log, which we just talked about, of 2 over log of 1 plus r. And this is log with a base 10. We use it, technically you can use log of any base, but we like log of base 10 because it has a place on our calculator. Yay! Just below the second value here is our button log. And so this is what we're going to use if we ever want to know the doubling time. We're actually going to skip around, sorry. And we're going to look at example 7 first, before we look at example 6. Example 7 says, suppose a virus is spreading at a rate of 8% new cases per day. Find the time that it takes to double. And so our R value in this problem is 8%. That's our growth rate, which we can express as 0.08. To find the doubling time, we simply just plug it into our formula. log base 10 of 2 over log of, if our R value is 0.08, 1 plus 0.08 is going to give us 1.08 inside of the denominator. And I'll go over here. Calculator already gives you little parentheses for log, for the location of log. Sorry, I don't know if you can see that very well. That's better. Oh, no, it's actually way worse. Okay, so log with a base 2 divided by log 1.08. We calculate this, and it's really, really close to 9, and so we're just going to approximate it with 9. Now, 9 what? Is this 9 days, 9 months, 9 years? That depends on what the problem told us. So remember that the problem should be giving us a unit of time so that we can give back a unit of time in our answer. It told us in here that it's growing 8% per day. And so the time that it's going to take to double the number of cases is 9 days. Something that's growing at 8% a day will double in 9 days. That leads us to the analogous discussion of half-life. So half-life is also an exponential model. We refer to this one, though, as exponential decay. What's happening is, over time, we're slowly but surely trimming away half, and then half of that, and then half of that number, until we get down to minute values. So before we do the examples that are here, and I give you a formula to use, let's just talk about how half-life works in a natural setting. Suppose I have 100 grams of medicine. Maybe it's, I don't know, some sort of an anesthesia, right? And we have 100 grams of medicine in my body, and let's say it has a half-life of 1 hour. So I'm just going to make a quick chart to show you how it's going. Amount and time. So in the beginning, we start out with 100 grams at time 0. Then, after 1 hour, I have lost half of the amount, so I'm down to 50 grams. Does that mean after 2 hours I have none left? No, because what I'm doing now is I'm taking half of this number here. And after 3 hours, I take half of this number again. Half of 25 is 12 and a half. And I can continue this process, taking half and half and half and half. So rather than having to do this by hand, particularly when the numbers don't line up very nicely, we have a nice formula. The half-life formula looks just like the doubling time formula. Q is equal to Q naught. The only difference is now instead of multiplying by 2 raised to a power, we're multiplying by 1/2, or 0.5. What power are we raising it to? That same power again. 1/2 raised to the little t over big T, and then we call this big T half, or the half-life time. Again, Q naught, our initial amount, little t, time, again, that's our input for time. T half is given, it's the half-life time. So now that we have a nice formula, looks very familiar to our doubling time formula, we can do example 6. Sorry for jumping around. 6 says, suppose that 100 pounds of plutonium-239 is deposited at a nuclear waste site. If the half-life of plutonium-239 is 24,000 years, wow, that's a long time, how much of it will still be present in 100,000 years. So our initial amount is going to be 100. We're going to multiply that by 1/2, raised to our fraction up here is going to have 100,000 and 24,000 in it. Question is, which one goes where? Always fill in the half-life one first. Told us that the half-life was 24,000 years. So that's our denominator. And we're interested in how much will be left in 100,000 years. So that's our numerator. Don't forget your parentheses. At this point, we can throw it into the calculator. We get 100 times, I just use 0.5 in the base for 1/2, but you could also do 1 ABC2 inside of there like that, and that would be fine too. Either one is okay. So 100 times 1/2 raised to and don't forget your parentheses here, otherwise you will miss this every time. Numerator is 100,000. Denominator is 24,000. And we see that after 100,000 years, I'll round to 2 decimal places. In this case, I will always tell you what you need to round to. I round to 2 decimal places, and I'll say 5.57. Don't forget your unit. Remember, this is a future value, so we should be looking at how much of something is left, and we are looking at plutonium measured in pounds. And so we're going to have 5.57 pounds left. Lastly, we look at that process of finding the half-life time, just like we did finding the double lifetime. We get a formula. It tells us that T1/2 is equal to negative log of 2 over log of 1 plus r. Remember that r is a growth rate or a decay rate. For the T1/2 problems, r should be negative because we are losing value. So the rate is decreasing. We want a negative r. So we'll look at example 8. Example 8 says, if the Russian ruble is falling in value against the dollar at 12% per year, determine how long it will take for the ruble to lose half of its value. So our R value in here is negative 12%, which we can write as a decimal, negative 0.12. So the half-life time, or the time that it's going to take for this to cut in half with a 12% loss over and over again, is going to be negative log of 2 over log of 1 plus a negative 12, or 1 minus 0.12. This becomes negative log base 2 over log of 0.88. Go back to the trusty calculator, plug in negative log 2. And with that, we divide by log of 0.88. And we get about 5.4. And what unit is this in? We are determining how long it will take for it to lose half of its value. Remember, it's declining at 12% per year. And so this is 5.4 years. It's going to take about 5.5 years if you're losing 12% for you to be down to half of what your initial value was. That's it for section 8B. And that's it for chapter 8. The most important things to remember in chapter 8, these 8 examples, which I'll post online, are really good ways of looking at the 4 different kinds of problems that we could ask. I could ask you about half-life time, doubling lifetime, modeling with linear or exponential equations, particularly half-life and double time as well. Be, be comfortable with all of these. Reach out if you have questions.